Welcome to the Joint Earth Observation Laboratory Seminar Series. Today's seminar is, as I said, joint with the Atmospheric Chemistry and Observation and Modeling. Apologies. My name is Jørgen Jensen. It's my pleasure to introduce our speaker today, EOL's Dr. Holger Vömel. Holger has a Bachelor's of Physics from Frankfurt University, a Master's of Physics from University of Heidelberg, and finally a PhD from University of Colorado. Holger has had a lot of experiences in laboratories for crystallography, a heavy ion accelerator, and nuclear physics. His PhD work was on humidity measurements in polar and tropical stratosphere. He continues to study water vapor and ozone as a research scientist at CERES after he graduated from University of Colorado. And in 2008, he took the position as senior scientist and head of the Gruen Lead Center. Here he designed, implemented, and managed the GCOS reference upper air network, which is Gruen. In 2014, Holger came to NKEOL, where he is currently a Scientist 3. He has also been a NASA Global Change Fellow, and he has a very large number of awards from NASA, NRC, and other institutions. Now we look forward to learning more about his work on ozone sonde measurement and their applications. Today we are using Slido to pose questions, which you can ask at any time during the seminar. The Slido window is located at the bottom of the presentation screen. Please do not be alarmed if you cannot see your question, because we are collecting all the questions that will be revealed during the question and answer session at the end of the seminar. And now, Dr. Vömel, we welcome you. The virtual stage is yours.
Thank you, Jan, for that nice introduction, and welcome everybody out in the ether for this virtual seminar. I'm going to talk about in-situ observations of ozone using electrochemical concentration cell ozone sondes, which have accompanied me for a good part in my career. And this particular picture that you see here is from a balloon launch in Costa Rica, where I've been PI and co-PI for the last 15 years, actually. And I'll show you a number of data from that site, because it's really, really interesting. Let me see. Before I jump into it, let me just give you a little outline what you should expect for the next 40 minutes or so. Just a little importance of ozone, how ozone is distributed in the atmosphere, and why do we care? Where is ozone measured, what networks there are. And then the core is a little bit more technical. How does the ECC actually work, which even though it is a 50-year-old instrument, is still a little bit of a mystery. So I hope you can bear with me on that part. There is some important developments in the last few years considering the time response of that instrument, which have quite some important implications, in particular on measurements, observations in the upper troposphere and lower stratosphere, which is my next point. And then, because it's actually an interesting little aspect, I also show you some results from volcanic emission observations with ozone sondes. And you might wonder how that works. And if you're curious, please stay with me. Before I really start, let me acknowledge some of my co-workers here, ozone and water vapor station at Costa Rica. Those soundings have been run by Jorge Andres Diaz, Ernesto Corrales, Alfredo Alan, very capable technicians and scientists, and they have made sure that the ozone sondes are being launched and give great data over the last 10 years by now. Henry Selkirk and Ryan Stauffer were and now are the PI of that project that I actually started like 15 years ago. I do want to acknowledge the Shadows data manager, Deborah Kolnich from NASA, and all other stations that launch ozone sondes and provide really, really great data. I also want to acknowledge the members of the GAR Assessment of Standard Operating Procedures of Ozone Sondes, ASOPOS. I'm not going to read them out, but I'll mention that ASOPOS report in my talk as well. So first of all, how does ozone look like in the atmosphere? How is it distributed? Most of you, I guess, know, but you have the well-known stratospheric ozone layer in the tropics. The peak and partial pressure is around 25 kilometers or so. You have a lot less ozone in the troposphere down here. The ozone layer, of course, is really good for us. We need this filter for UV radiation, but we do not want the ozone down in the boundary layer, where it's a sign of pollution and smog. Here, particularly in the tropics, ozone is a great tracer for exchange process between the troposphere and the stratosphere. And here in the tropopause region, that's where you have the lowest concentrations of ozone, or among the lowest concentrations of ozone in the atmosphere, which also means it's the hardest to measure right there. Very often, the ozone is measured as ozone column. So you basically integrate all ozone from the surface all the way up to the edge of space, basically. If you take all of the ozone molecules and compress them to a pure ozone layer at standard pressure and temperature, that layer of ozone gas, pure ozone gas, would only be 3 millimeters thick. So about the thickness of 3 pennies. So the amount of ozone totally is actually rather small, and therefore accurate measurements are equally quite challenging. And I want to give you a climatology here in Costa Rica. As I say, I have a bunch of data from that particular site, but the tropics are particularly interesting. So this thick line here is a climatological tropopause, is a small seasonal variation. Ozone layer up here, maximum at around 25 kilometers. And then you see here a seasonal maximum in July, August, September, which is actually quite interesting. That's in the second half of their rainy season. I'm not going to go into great details, but just to give you a flavor of how ozone climatology looks like at a particular site. As well, you have very low ozone concentrations right in the boundary layer. And then here at 3 kilometers, sort of a mixed bag in this particular plot here. And I'll go more into detail why that is at the very end of my talk. This is how climatology looks like. You can learn a lot about exchange processes between the troposphere and stratosphere from these plots. But it might also be interesting to look at long-term trend series. And so here's the same data set now as ozone mixing ratio anomaly here, time axis on the bottom. Each data point is a particular layer and a particular sounding. So to make sense of it, we actually do need to do a lot of smoothing. And I grouped here the data by particular altitude bins, 2.5 to 4.5 kilometers, 5 to 13. So this is basically free troposphere. That 14 to 18 is sort of roughly UTLS region, upper troposphere, lower stratosphere. 18 to 20, lower stratosphere, and then some stratospheric layers. What sticks out in this 2.5 to 4 kilometers, you have a big anomaly down here. Again, I go into that at the end of my talk, where that comes from. And then you see sort of a big drop off here, change in almost 10% in ozone, 2016 to 18 roughly, and then a recovery. This plot has actually raised a lot of discussion and a lot of debate in the ozone sonde community. And by now we know this particular drop here is actually an artifact of the instrument. We don't know yet exactly where it comes from, but it triggered a lot of research, a lot of thinking, what's going on with the sondes. And therefore, I'm going to explain a little bit more how the instrument works, what factors play a role, and why it is actually quite difficult to make measurements on that level. Costa Rica is the most extreme side that these has dropped. A few other stations see it similarly. But again, I'm not going to go into great detail here. That's actually material for a different talk. So globally, where do we measure ozone with ozone sondes? Here's a map with just a bunch of balloons. These are mostly operating ozone sonde stations. A big number, or an important number of stations is right here in the tropical belt, right? These stations. Costa Rica right here. San Cristobal Galapagos, a site I worked with, they stopped 10 years ago. Quito right here is starting up right now. There's a station here in Kenya, a station here in Indonesia, and then some island sites, Tahiti, Fiji, Samoa, where ozone sondes are launched in the tropics. Hawaii right here. Boulder is, of course, right here, an important site in Europe. These are all for routine monitoring. Of course, the polar sites here in the Arctic and the Antarctic. South Pole also has a site. They're really important for ozone hole research. So ozone sondes are used at about 60 sites or so, and typically launched somewhere between twice per month to, in the extreme case, maybe 3 times per week, or seasonally at the poles. It depends a little bit what the focus is on it. Over the last 20 years or so, this sonde network has supported the validation of roughly 20 or so ozone instruments on satellites. And they're also used to calibrate ozone lidars and even profiles from commercial aircraft. There's a YAGOS program on measuring ozone on commercial aircraft. The sondes, because the sonde record is really long, at some stations now are reaching almost 50 years, they have a very unique role in detecting drifts in ozone profiling satellites. Some of those satellites now lasting well over 10 years. Aura MLS, most importantly, is still up and measuring. Because of this duration of data records, the satellite and trends assessment community by now demands accuracies of something like 5% or better from the sonde data. And that's really challenging. And the climate community actually demands a stability of 2%. And that's probably not quite what sondes can achieve. Now, across these 60 sites, there's a significant challenge. And that is that there are sondes used from 2 different manufacturers and 3 different sensing solutions, SST sensing solution types that are being used. And the sondes with varying instrument SST combinations are launched together either in the field or have shown in simulation chambers to give different readings in different parts of the profile. So it is a big challenge to homogenize these different combinations of instrument and sensing solutions. I go into that in just a second. So as a result, the ASOPOS activity was formed a little over 10 years ago, not quite sure how long it actually originated, but over the last 4 years or so, it was very active in the second review of assessments of standard operating procedures for ozone sondes. As I said, it's an international committee to assess the performance of the current ozone sondes and to define the official WMO GAR recommendations for station operators and for software providers. A number of publications have come out of this activity, most importantly by Herman Smith and Ann Thompson as editors, the ASOPOS report, which is in print right now and should show up in the next month or so. I'm not quite sure how long that takes them. Ryan Stauffer at GRL, he has a paper about this ozone drop-off that I showed you in the earlier figure. Dave Tarasek discusses more the overall uncertainties, and I had a paper discussing the time response. And I will focus here in my talk a little bit more about the time response, because that's an important process for boundary layer and for upper troposphere, lower stratosphere measurements. So, how does an ozone sonde work? Even though it's a 50-year-old instrument, it's still a little bit of a mystery, but I show you the basics that are actually quite well known. You have a pump here on the left that pumps air into an electrochemical concentration cell. That ECC consists of 2 chambers. On the left, you have the anode. On the right, the cathode. Air is pumped through the cathode, does some chemistry in here, which changes the electrochemical potential between those 2 cells that are connected by an ion bridge. And changes in the electrochemical potential, they trigger an electrical current that can be measured and that restores that electrochemical equilibrium. To make that work, in the anode, you have a saturated potassium iodide solution, which is neutrally buffered. On the right hand, you have typically a 1% potassium iodide solution, also neutrally buffered. And I put a little star in here because that's where one of the variations already is. Some sondes use exactly as I say here, 1% neutrally buffered. Other sondes use only 0.5% neutrally buffered. And the third type is again 1%, but only 1/10 of the buffer. So the chemistry happens mostly in the cathode cell. And what happens, you have a reaction between ozone and iodide here. So in this aqueous potassium iodide solution, ozone reacts with iodide, converts it into iodine. And at the cathode, because of the change in electrochemical potential at the cathode, you have a reduction reaction where iodine is reduced back to iodide, and that process takes up 2 electrons. These 2 electrons, that's that external current that you can actually measure. So far, so good. The basic chemistry says you put 1 ozone molecule in, you get 2 electrons out, and the rest is fairly simple math, and you could measure ozone directly. However, there are some reactions that involve the phosphate buffer, and they also generate some additional free electrons that are being measured. And so there's a slight over measuring depending on the phosphate buffer. I'll show you some examples of what that actually means. And there are some interference reaction in some unusual cases. And one predominant interference reaction is SO2. If you have SO2 in the atmosphere, that reacts and forms SO2 4 2 minus, and again 2 electrons. And those 2 electrons, they reduce the iodide back to iodide. And so they basically reduce the current that's being measured. So this interference reaction masks the amount of ozone that the sonde actually sees. So here's the basic ECC equation. There's a lot of constants in there. Here, the front, some constants. Here is the measured pump temperature and the flow rate. This term is basically just to know how much air is going through the pump. And then here is the current generated by the cell that you measure. And historically, there is what we call a background. I actually don't like that anymore, but there's a background that's subtracted and corrected with some efficiencies. Historically, this efficiency correction was called a pump efficiency. Now we call it like total or empirical efficiency correction. The challenge for really accurate measurements is that we use 3 different sensing solution types. There's actually more, but they're not very common. The others, those 3, they're quite widespread across the network. So SST 1.0 is this 1% full buffered solution, and that is used in sondes from the manufacturer Science Pump Corporation, SPC. The other one is almost the same solution, except it's diluted by a factor of 2. And that's used in sondes from the other manufacturer, NSI. And there's a second solution type, SST 0.1. It's again this 1% potassium iodide, but only 1/10 of the buffered. And it's also used in the sondes from NSI. So all of those use the same equation, but this efficiency is tuned. So this total efficiency correction, it combines the stoichiometry differences of these 3 solutions and the physics of the pump. We know that the pump becomes less efficient at higher altitudes, so we correct for this. And this correction has been empirically tuned to the sensing solution type in the manufacturer. So you have to be really careful which efficiency correction you use with what solution and what manufacturer. This background current is measured prior to launch, but it shows large variations, and I'll show you that in a sec. And again, there's other solutions that have been used. And so to really get consistent homogeneous data records, that takes a lot of work. And over the last 10 years, there has actually been a large homogenization effort to make sure that all stations, or at least the stations that participated in that effort, produce consistent data that can be used for trend assessments. So let's look first here at the efficiencies. The efficiencies is that factor here, this eta t here. And there are basically 5 different curves that are used. They are pressure dependent, and here this efficiency factor varies from 1 to something like 0.8. So here's almost a 20% correction up here at this 5 hectopascal pressure. 10 hectopascal, it's like 13% correction here or 5% correction here, depending on which one you use. Now, the curves from Johnson, that is purely measured pump efficiency. So that is something we can actually measure in the lab. You take the pump, put it in a chamber, and measure how the efficiency of the pump decreases at lower pressures. So the ability for the pump to move air. This here is literally an empirical correction that was basically tweaked to match the validation observations, and that is used for the other manufacturer, actually for one solution manufacturer combination. The more yellow one is for the second solution manufacturer and solution combination. So this is highly unsatisfactory that we have something like that, and would be better if we could understand this better. Here's the background. It is this factor back here. And here's just the statistics from a whole bunch of stations, what background values are being reported. And I'll show you in the next slide how that's actually being measured. So many stations report a fixed number of 0.05 microamps. So the cell current is in the microamp range typically, 0.04, 0.03, and there's some distribution here. Again, this looks somewhat strange for the behavior of a sonde. Yeah, it should be either sort of a fixed distribution or however. This is not very desirable as well. Here's actually a setup, how the background is measured. What we do in preparation, the sonde is connected to what we call our ground check unit. It generates ozone and it has a built-in filter. So we can either expose the sonde to ozone, or we can switch in a filter and pump ozone-free air through the pump. As part of the preparation then, this is the steps that are being taken. So the sonde is turned on at some point and it generates a small amount of current. This is with a ozone filter, so there's ozone-free air going through the sonde. Then on this ground check unit, we turn on the ozone generation, and so that about this the sonde generates about 5 microamps of ozone, and this for something like 5 to 10 minutes. And then at some point, the ozone is switched off again, back to a filter, and we measure this decay. This is just one example. This is done at every station before every launch. It always looks like that. Here is the statistics of just a whole bunch of them, and here actually 2 different solutions. The red one is this full buffer, so the SST of 1.0, and the blue ones is the SST 0.1, so same amount of potassium iodide, but different amounts of buffer. And that we get different reactions here simply because that buffer is different tells us, oh, that buffer actually plays a role in it. And that's why I said earlier that buffer does contribute to the signal that we measure. We just don't know exactly how. We don't understand the details of the chemistry there. But what is done then to measure the background, just arbitrarily say at 10 minutes, we measure what's the cell current generated by the pump, and we call this our background. But that actually is somewhat arbitrary because the cell current actually keeps continues decreasing. This is a log scale here, so it keeps decreasing for well over an hour. We also see there's a really fast drop-off right here. And so which one is the background? So this constant number that's subtracted in the ECC equation based on this measurement is rather arbitrary. And personally, I think it's actually incorrect. So I believe that this concept of a constant background is invalid. Rather, what we see here, it's a superposition of 2 different time decay constants. This, the very fast drop-off here is actually an exponential decay as well, with a time constant of about 20 seconds. And this slow decay here, so drop-off with a decay constant of about 25 minutes. This one, we understand, the fast one, that's really our chemistry between ozone and potassium iodide. And this here is involving the buffers. So we have two different superimposed reactions with different time constants. We also know that the two sensing solutions give different readings in the slow path, and so there is some additional chemistry happening that involves the phosphate buffer that we can account for. So once we recognize, hey, there's actually two different time constants, two different exponential decays here, we can use that information to come up with a time response correction. We can correct for those two different time constants. And so the basic assumption is our measured cell current has a contribution that comes from our fast reaction and one that comes from our slow reaction. And we understand by now that the fast reaction, the potassium iodide reaction, contributes well above 90%, 90 to 95% of the measured signal. And the slower reaction that are related somehow to the buffer and the other side reactions, they contribute less than 10%. I don't go through the gory math, how this is actually set up to solve it, but this equation can be solved iteratively. And what we are after is actually the fast reaction contribution. So basically our contribution in the reaction of ozone and iodide. And we want the steady state of that particular reaction. That one we can plug back into our ECC equation. So you see our background dropped off here. We just have the steady state after this. And we modified our pump efficiency, In fact, our efficiency correction is just our pump efficiency. So just purely physics of the pump and no longer stoichiometry in the cell. The stoichiometry part is taken up here by the slow reaction. So the algorithm calculates that slow reaction contribution and replaces the background. And that captures the contribution of the buffers. And it uses the same pump efficiency correction for all zones and solutions. So with that, it's no longer necessary, oh, I have this manufacturer and this solution, I need that efficiency correction. It uses just the measured pump efficiency for all of them. There is, just as a note for the true experts listening in, there is an observed difference between the two sound manufacturers, which is not captured here. So here's how does that look like if I apply this processing in the lab. And so here I have one lab example where on the bench, we can generate step changes in ozone. And these step changes in ozone, they're actually measured by an ozone photometer right here. And it's this blue curve. So this is the ozone that we stick in. So real nice step changes generated and measured. This orange line is the raw measured ECC mixing ratio conventionally without time response. And you see a little bit of over measuring here. Here's some slower drop off there, and the same thing here, the same thing on the upwards steps. With a proper time response correction, you get this red curve here, and it almost follows nicely our step changes. So we basically can recreate the artificial step changes with our time response corrected ECC measurements. And just to show you here the differences, the ECC time response corrected minus the ozone photometer is almost a constant curve here, just a minor offset here. Without the time response correction, you have some constant bias here. That is that stoichiometry due to the solution, and it changes depending on the amount of ozone that you put in. So this is how that looks like. Also, I want to point out the slow reaction contribution is this pinkish line here. That's what was background, what we assume was a constant number. It's anything but a constant number. So here in Julich, we actually ran a large number of simulation chambers. Now we didn't just do step changes. We really ran a full profile in a simulation chamber, so we could simulate pressure, temperature, and ozone, and of course had an ozone photometer in there as reference. And so the average of all of those difference, ECC time response corrected, and here minus ozone photometer, and ECC not time response corrected. So that not time response corrected is the blue, time response corrected is the red. So you see there's a significant improvement, and most importantly here in the upper troposphere, lower stratosphere, something like 10% change. So it actually works if we apply this to lab experiments. So how does that affect individual ozone profiles? Here is a profile from Costa Rica. That's important to understand. I show it in cell current. You could translate it more or less into partial pressure, not into mixing ratio, but into partial pressure. So you have your ozone minimum in the upper troposphere, ozone layer right here. You have some nice features there. But what's important to understand, this is this contribution from the slow reaction. And this is the original, what we used as our constant background. And the slow reaction contribution is very different than our constant background. It's lower than the constant background in the troposphere, and it's higher actually in the stratosphere. So if we apply this, it will change the structure of the profile. And also look at the roughly the relative ratio here. A constant background here, this is 0.02 microamps compared to 0.08. So this is about 25% of the signal. Whereas this one is maybe less than 10% of the signal. So this correction here in the upper troposphere is actually quite large, or the change in correction. The same profile, just extended a little bit because this has a nice feature. So you actually see what's happening. So I expand from this measurement the layer from 10 to 15 kilometers, where we have some nice double structured layer. The dark blue is our conventional ECC processing, no time response correction. And the red one is the final time response corrected profiles. And especially I want to draw your attention here to the layer at 12 kilometers to really show what happens with the time response correction. The altitude of the peak gets pulled down a little bit. Here, this gradient gets pulled down, and that's simply time response. So we correct for the lag in the sun. And also the amplitude of the peak gets enhanced. So that minimum here is lower than the actual original reported minimum, and the maximum is a little bit higher. So what that means, features get enhanced, gradients get enhanced, and the profile gets moved down a little bit. And up here between the 14 and 15 kilometer region, there you see the original ozone is quite a bit lower. That is the difference in slow reaction contribution versus the original constant background. Here with that constant background, we subtracted much more than we should have. So that's actually a nice visual representation of what the time response correction does. And it's actually not negligible. It also happens near the surface, so in the boundary layer, where you often have very sharp gradients. Here, this dark blue region is right here. For the moment, ignore the difference between those two curves here on the left-hand side. So this is the originally reported gradient with a proper time response correction. That gradient becomes a lot steeper than the original non-time response corrected. And the difference between those two different curves, the pink and the orange curve here on the left, is some assumptions on what happens just before launch. Because there's a time response, it also matters what happens before launch. And so what assumption I stick in there matters a little bit, but those assumptions, they decay quite rapidly. So within 500 meters or so, the assumptions of what happened before launch, they go away. So if we do not record or report the measurements before launch, it's a little difficult to do the time response correction properly. So that also has some implications on the operational procedures, which means for boundary layer measurements, it's really important to record and process the measurements prior to launch. So let me show you what the effect of the time response is for Costa Rica and a bunch of the other tropical stations within the SHADOWS network. So here's Costa Rica. It's 1%, 1/10 buffered solution. So it's not as strongly buffered, so probably not as strong a correction here. And with that time response in the troposphere, only a couple % increase. In the UTLS, upper troposphere, lower stratosphere, the reported ozone increases on average by about 7% or so. And in some, this is a ±1 standard deviation. So something like 12 or 15% as one standard deviation. That also tells you there are probably some extreme cases where the correction is even larger than that. Also note here, right in the boundary layer, the correction actually is quite large, and we get increases 20–30% near the surface as a result of the time response correction. At a number of other stations that use the 1% full buffered solution, so a stronger side reactions. Here we actually have a decrease in the middle troposphere and the free troposphere, and again this increase in reported ozone in the UTLS region. So here the change in the ozone profile structure is even larger than with the other solution type. And there is a third solution type. I don't show it individually, this SST 0.5, so this 1% full buffer diluted by a factor of 2, that is sort of in between. So how the structure of the profile changes depends on the solution that's being used. That is a big takeaway message. And in the UTLS, all of them report too low, and the ozone actually is most likely a bit higher, 5 to 10% on average over this entire region. Now, very often I look right at the tropopause. What happens at the tropopause? And so before, in the previous plot, I just did my binning by altitude. In this particular figure, I actually did the binning relative to the climatological tropopause. So I basically lined up all profiles so that the tropopause lines up. And that's actually quite interesting, because now I have a much stronger increase right at the tropopause. And that is a result because my selection, my shifting my profiles up and down, I artificially always select a layer where ozone is increasing. There's always some wiggles typically in the UTLS region, but by picking the tropopause, there's almost always an increase. And so here I do not average out anymore layers where the ozone is decreasing a little bit with ozone is increasing. I always pick gradients, and gradients get enhanced. So at the tropopause, if you look at exactly the tropopause, changes of 10–15% are more likely than the 5 to 10 that I said earlier. And it also depends on the amount of ozone. So here I just picked the ozone mixing ratio at the tropopause, and look at what's the relative change in ozone as a result of the time response correction. And so, yeah, it's here. I have here 6–7%. There's a guiding line here, but it's 10%. But look at these regions here where you have low ozone mixing ratios anyway. The change can be up to 90%. So the change in ozone at the tropopause, in particular at really low ozone concentrations, can be quite large. And that is actually answers an old vexing question that we had not quite, or a little over 25 years ago. There was the campaign CEPEX. I was actually on the boat launching those ozone sondes. It was my first big field campaign. And very surprisingly, we saw in the upper troposphere, lower stratosphere, upper troposphere, tropopause region, ozone values basically reaching 0 or very close to 0. And that was always puzzling. What makes this ozone so extremely low? What we didn't really appreciate was this time response effect. And so because ozone is so low and our constant background that we use was actually rather large, these numbers came out quite low. Had we done a proper time response correction, we would have gotten here these red profiles in between, and all of those low data points, they would have disappeared. And this is one example here. On average, our correction in the tropopause region is on average actually almost 90% or 100%. So basically, these near zero ozone observations at the UTLS, they are probably quite questionable. It's much more likely that you have a nearly constant mixing ratio profile throughout the troposphere, reaching all the way to the tropopause. So no extra processes needed that destroy ozone up here. Okay, let me change subject a little bit because we're still in the functioning of the sondes, and show this profile from Costa Rica. We see this quite frequently. Now I just show the lower troposphere, 1 to 7 kilometers, and we see layers between 2 and 4 or 5 kilometers where there's almost no ozone. At least that's what our ozone sondes tell us. And again, they're quite frequent, but as I pointed out earlier when I described the chemistry, SO2, sulfur dioxide, is an interference gas. And that comes out of volcanoes, and Costa Rica has volcanoes. And I show this particular sonde because here we flew in parallel on the same balloon, a second ECC that had a selective SO2 filter. So this second sonde sees the same air, except SO2 has been selectively filtered. So below that layer and above that layer, we see exact same amount of ozone. In that layer, we see all of this is due to SO2. Well, that's of course really nasty. It's like, we don't want that. But then we figured out, well, maybe that's not such a bad thing. Here is the satellite overpass from the AURA satellite, the ozone mapping instrument. And we see right here, there's a little signal in ozone. And those triangles actually indicate volcanoes. This here is Turrialba volcano right there. And our launch site at the University of Costa Rica in San Pedro is right there. We're right under this where OMI detects some amount of ozone, some amount of SO2. And so we actually see this SO2 vertically resolved. This is one example. Here's another example, and that is even cooler because here our reference, this was a couple of years ago. Here the reference instrument is actually on the ESA Sentinel-5P TROP-OMI. TROP-OMI is the instrument, which has a much higher horizontal resolution. They only have like a 7-kilometer horizontal resolution. And here, this particular sounding was launched at University of Costa Rica Fabio Baudrit site, a little bit further to the west. And in fact, this launch that was my title slide is this particular launch. Here we saw a different SO2 plume coming from the volcano Poas, not from Turrialba. So we were really fortunate when we launched right there. Poas had actually quite a significant eruption, and we caught it in our ozone sonde. And again, so strong layer, no ozone indicating SO2. What is really interesting, we can sort of extrapolate the line here. If we just say this straight line from that edge to that edge, that's where the ozone should have been. We can integrate the amount of missing ozone and say, hey, that's actually SO2. So we can give an estimate of how much SO2 is in that layer. And so here it's about 6 Dobson units, the same Dobson units as we use for ozone. 6 Dobson units SO2, rough estimate from the ECC. It could be more. And TROP-OMI just actually rails here in this particular one at 2 Dobson units. It might well have been more. So this is not too bad. We actually have over 200 soundings that show these SO2 layers. And most of our soundings were done here at the UCR San Pedro site, which is on the eastern edge of San Jose, Costa Rica. We have used a different launch site. Fabio Baudrit was right here. There's Poas volcano right there. We launched a bunch of soundings at the early parts of our program 15 years ago at Alajuela and as well as Heredia. But for the last 10 years, we've been at UCR in San Pedro. And the wedges that I show here is the wind directions. Where do these SO2 layers come from? What's the wind direction that we see when we see one of those layers? And the color coding is the median SO2 column in this wedge from all soundings. And so clearly, yes, all of those come from the direction of Turrialba. And this is probably something really interesting for anybody doing mountain meteorology or boundary layer meteorology. Turrialba is about 3.3 kilometers high. Right here is another volcano, Irasu, about the same altitude, 3.3 kilometers. This one is inactive, does not emit anything. So we know it comes from Turrialba. There's some monitors here where people monitor on the ground. And so this is a volcano. There's a valley right here, and there's a valley right there, to the north and to the south of these two volcanoes. So exactly how the emissions come from Turrialba to San Pedro, how they distribute vertically, that itself is a very interesting scientific question. And this is actually my last slide. We've launched these soundings somewhere between weekly to monthly, depending on the funding and the program that we operated under. Those red dots are our ECC ozone sondes, the SO2 column that we estimate, so these little notches added up. And the blue dots are from Ora-Omi overpasses, the lower troposphere SO2 column estimates. And you actually see here the activity of the volcano, Turrialba volcano, which went through some cycles. So when we first started, we saw the first SO2 layers right there, but Turrialba was not very active. We saw the increase in activity in 2008. We certainly saw the strong increase in activity in 2010. In fact, we had one layer where we saw 16 Dobson units. We lost something like 6 or 7 kilometers of ozone due to the SO2 in the air. And then in the last couple of years, especially the last year, Turrialba has calmed down a fair amount. And we see that as well in our ozone soundings, that we detect these layers a lot less frequently. So it's actually a really fascinating thing that a project that was not designed at all to look at SO2 actually can say something about volcanic activity in a nearby volcano just due to the interference reaction of SO2 with the chemistry happening inside the ECC. So with that, I'll come to a close. The summary. The time response correction is important and allows separating processes in the ECC. So the efficiency correction becomes a pure efficiency correction and no longer has these empirical factors in it. That slow reaction takes up all of that stoichiometry and replaces that background. And again, the stoichiometry in the processing is really reduced to a constant stoichiometry coefficient that we can possibly even measure in the lab. The structure of the profiles that we report with the ECCs, they change slightly depending on the solution recipe. And in particular in the UTLS and in the boundary layer, ozone gradients are generally becoming stronger. At the tropopause, mean increases up to 15%, but individual profiles may report increases up to 90%, again, depending on the profile gradient and what was the original background that was used in the original processes. With the time response correction, I believe actually ECCs may achieve eventually an uncertainty level of something like 5% in the profile. But that still has to be validated. But so the original goal or demand by the satellite community, I think we can achieve, but the time response correction is absolutely vital for that. And the last point is really that with the ECCs, since they are sensitive to interference gas SO2, we can monitor volcanic emissions as a byproduct. And with that, I thank you for your attention, and I'll be happy to answer any questions that you may have. Thank you.
Well, thank you very much, Holger. That was a really interesting talk. I learned a lot. We have now time for some questions. We have plenty of time for it. We can, so you can all answer them on Slido at the bottom of your screen, but we already have the first one here from Megan Still, who asked, just to clarify for my own understanding, is SO2 the cause of the change in the ozone concentrations below, in, and above the tropopause? That is really interesting.
Thank you, Megan, and thanks for making me clarify this particular point. So the SO2 is an interference reaction of ozone and potassium iodide inside the ECC, inside the cell. So in the presence of SO2, our sonde reports incorrect ozone amounts. Ozone is still in the air, so the ozone concentration has not changed. It's just that the SO2 masks the signal that the ECC would measure. So the presence of SO2 makes it look like there is no ozone. Ozone is still there actually because it's not affected by the emissions, but it affects our ECC. So the SO2 only plays a role in significant amounts. So if you're downwind from a volcanic emission and you see these low or zero ozone layers, you know, oh, we see SO2. Ozone is still fine, but we can't measure it. We're measuring SO2 instead because it interferes with our reaction. It also plays, I didn't point this out, if very near the surface, if you're in an environment that has a lot of SO2 emissions, coal-fired power plant or something like that, you would have the same effect. In the upper troposphere, stratosphere, unless there's, of course, volcanic eruption going that high, SO2 does not play a role. So all the changes in the upper troposphere and stratosphere, that's all time response, and that's a different process in the ECC.
Okay, thank you. Do we have a next question? And this is from Jim Swap. In the Julich chamber, do you stipulate temperature, pressure, and ozone using standard atmospheric values?
Yes, Jim, that is correct. So in the Julich chamber, they could simulate a true ozone profile as you would observe it in the atmosphere. So temperature, pressure, and ozone was simulated at the same time. I should have showed one of the examples, but for time reasons I didn't. But yes, it's a true simulation of the entire profile and roughly the same time as well. One thing that was added in the Julich chambers that twice, once in the troposphere and once in the lower stratosphere, ozone was artificially set to 0. And that with a purpose to evaluate the time response. So far, I don't think anybody has looked in great detail at that. I've looked a little bit into that. It basically confirms what I've reported here, but they added that to those measurements. So if you look at the raw measurements, you actually see a typical ozone profile, and suddenly for 5 minutes, it jumped to 0 and then back to full ozone. But yes, and in the last 2017 Josie campaign, the focus there was on tropics and mid-latitudes. So it was tropical and mid-latitude profiles that was simulated. I think 2010 or whenever the last previous Josie was, there was more focus on mid-latitude and polar profiles. So they can actually simulate or select which climatological region they want to simulate.
Okay, thank you. Next question. And Megan Estelle says, thank you very much. Do we have any more questions? I actually have a question here, Holger. Early on, you showed, I think, a climatology from Costa Rica. And in the lowest 5 kilometers so, I don't know if you can bring that a particular slide up again. You kind of showed a variation of periods that looked like maybe 6 weeks or so. And is, yeah, that one there to the left, number 6, no, up above.
Yep.
Yeah. When you look down in the lowest, maybe it's closer to, sorry.
I went to the wrong one. I apologize. Where am I here? Okay, I'll leave it.
Yeah. If you look down in the lowest 3 kilometers or so, you see a variation that is of the order of 6 weeks, or at least in what looks like the summer months here. So is that the Madden-Julian oscillation that creates natural variation in ozone, lower atmosphere?
Thank you very much for pointing that out. This here, what you see here, this is actually already that volcanic interference. So these layers here, they are these 0 ozone layers. I didn't filter them out. They're in there. And they happen purely random whenever we see them. And they create this layer. So this is not any dynamical structure. This is actually just a random observation of our SO2 interferences.
Okay, volcanoes, thank you.
Yep. In any other station, we could probably say something about the pure dynamics, not in Costa Rica, because we have this volcano 30 kilometers downwind.
Yep. Okay, thank you. And a comment here and question from Brad Palm. Thank you for a very interesting talk. Do you expect the same time response correction could be applied to all previous ozone sondes or could there be any systematic differences between suns from different locations and times?
Thanks, Brad. That is a very good question, and I'm actually working on this. In fact, I have already reprocessed all of the shadows data, and in principle, it should be possible to do it for almost all sounding data. However, there's a couple of caveats to that. One is we need to know exactly what was used. So we need to know the sensing solution type. We need to know if we can, it would be really good if they measured the fast time constant. This is part of the standard operating procedures now, measure this fast time constant. And a number of stations have done that and have done that for a long time. But there are a good number of stations that do not have that. And in other stations, I ran into the problem that data are only reported as function of altitude and you don't have a timestamp. So if you do not have the data with time, then there's no way of doing time response correction. In the shadows archive, a number of stations, they do have a timestamp, but it's obviously incorrect. And so I'm not quite sure what was, actually I do know a little bit of what's the origin of that one. But if you don't have a timestamp or if the timestamp is not quite correct, then you can't do it either. So it really depends a little bit what data you have available. The best is, of course, to do it from complete raw data if they are available. Then it should be possible to reprocess everything. But what's not always captured is the sensing solution type. That is really important because that's one of the parameters that goes into it, because you need to know what the stoichiometry is. But yes, I expect it can be done, but it is not as trivial as it sounds.
Okay, thank you. Any other questions? Okay, going 3, 2, 1. Well, in that case, I want again from all of us to say thank you to you, Holger, for such an interesting talk. That was great. Thank you very much.
Thank you, Jorn. And if anybody has a question, please feel free to email me. I'd be happy to answer. Thank you.
Thank you. Bye-bye.
All right.